So this talk is Lambda HardCore. Now, before I start about the talk, who am I? As you see, I'm just Java developer, JVM developer maybe better, a wizard and an architect. I spent 17 years of my professional life with JVM-based techniques. Before that, I was programming C++, and generally I have a lot of Pokemons on my list, so things I played and I hate. Okay, it doesn't matter. I work for CSS Insurance, so that's a company. We are located under this beautiful mountain over the lake in Switzerland. The name maybe suggests that, but that's not true. We don't insure your style sheets yet, only your health. But it's what's funny. The company was created in 1899. Do you think we have a lot of legacy code? Oh, not that bad. Quite honestly, for us, legacy is like Java E5. But okay, that's not the point of this topic. Okay, so agenda. What is the topic? So first of all, warning: if some of you came here to hear some details about Java 8 lambdas, you will be quite disappointed. It's not about Java 8 as it. Not about anything from JVM, whatever. So this presentation is basically for your regular job completely useless. I even say it would be good if it was useless, because otherwise you might get into the trouble. But even though it's not it should be fun. And this presentation is about the basic fundamental question, what is a number? And also, generally, what is a lambda calculus? Well, lambda calculi. Yeah, people call it differently. And then we'll do this thing in Java. Why? That would be a good question. Why to do it in Java? And then we'll have some fun. Okay. So the point of this talk is, maybe I'm not a scientist. One thing, sorry for that. You may think I am, but I'm absolutely not, so it won't be very, very scientifically correct, everything. Otherwise, I would have to spend a couple of weeks here. But I've studied mathematics. There is a reason why I've studied mathematics, just because at the moment I was choosing my studies, I was doing this thing on a Commodore 64. You know, who had for Commodore 64? Yeah, so if you were programming Commodore 64, that was really like, well, masterpiece. So at the beginning of my studies, I decided, come on, there's nothing in computer science I can learn. So it's just absolutely nothing, because I know that. And my colleague could do this on his PC, so he had the same problem. Oh, come on, he said, I will learn nothing more, because that's the most important thing in life. So because of that, he convinced me to go to study something really challenging, that was math. And that was the first lecture on this math studies, that 0 is indeed different than 1. So the professor was really doing a proof that 1 is different than 0. It took like 15 minutes, a lot of whiteboard. And after that, I realized, first time in my life, I've seen that those numbers are really different. How cool. But first time in my life, I have doubts about this. Nevertheless, okay, there is a proof, and mathematicians do that. After seeing that, I realized this study is going to be really terrific. That's great. Okay. Yeah, so the question is, where did this proof come? Yeah? What is the number? Who knows what is the number? Who can tell me what is the number? What? Yeah, that's one of them. Do you know any other numbers? Yeah, that's the problem. Yeah. So what is the number? And it is so stupid and fundamental question that it is very hard to answer. So maybe let me present you that those are 2 bottles of water. They represent 2 as a number. Okay. That's 1 bottle, 1. No bottles, 0. Okay. 2 bottles, great. But you see, that's okay to represent numbers with bottles of water. That's quite okay. That it's only the problem is if you have numbers like 100 or 200, you need a lot of water. And it starts to be heavy mathematics from 1000, yeah? So that's not perfect idea to represent numbers. So there's other idea. And by the way, let me see, there is a coin here. It's very important. It's 2 Polish zloty. And from mathematical perspective, it's really crazy, because it's one coin and represents 2. What the hell, yeah? So there must be something crazy with numbers. So what is the number? And mathematicians started to dig into that problem, because that's very useful for our life, to find out what is the number. And there was this concept, yeah, maybe we don't have water, we don't have coins, we have nothing, because this represents Big Bang, the beginning of the universe. Let's pretend it never happened. We don't have universe. We are so unlucky. And even there is this alternative theory. The universe was created by the flying spaghetti monster. So let's pretend, for some of you, there was no flying spaghetti monster. Yeah, let's imagine that. Yeah, so universe wasn't created. We have no bottles of water, no apples, and nothing. How is it even possible? Yeah, that in this world we have something? And mathematicians came to the idea, yeah, there exists something, let's call it set. And let's not define what the set is. So you've heard about sets in school, yeah? Set of something, yeah? So do you know any set that you can define in a universe that wasn't created? Can we construct any set? Who knows? Empty set, exactly, great, you are great. So you've started, really, that's the start of whole mathematics. Empty set. The universe wasn't created, doesn't exist, but we can discuss about empty set. How cool. Okay, if we have an empty set, we have something. We are right now like gods, we've created something. We have one thing, an empty set. How cool. So right now, we can create set which contains this thing, because we have something, one thing, empty set. So if we create set containing empty set, we have second elements. We are so powerful. Universe wasn't created, and we already have constructed 2 things. How cool, yeah? So we can go further. This is the definition, but just forget it. Let's see this thing. This is a set containing an empty set and set that contains empty set. That's a mathematical procedure that allows us to construct sequences. And by the way, these sequences we can call the empty set is 0, the set containing empty set is 1, this thing is 2, and this operation that allows us to create the next element in sequence is the successor. And this is basically the fundamental, I would say, theory that leads us to how to construct natural numbers, and this is the standard mathematics that you've learned from school. Maybe you've never discussed this, maybe you have, it depends what you've studied, but yeah, it works. And it worked pretty well. It was like designed more than 100 years ago. It was quite okay for a couple of years. And why, the question is, why mathematicians really were so crazy to dig into that things? There was a goal. There was a really holy grail. Because the idea was, let's define this mathematics pretty well, so that every fundamental brick, everything that we discuss is precisely defined. What is a number, what is an operation, like plus, whatever. If we have this, we have all these building blocks really well defined, we may get something really crazy. We may get to the holy grail that maybe you would be able to build a mathematical procedure, whatever, an algorithm that would tell us if a given theorem, so let's, like Pythagoras, whatever, is true or false. Just automatic machine that will tell us is something true or false. That was the initial goal. Let's build such machine. And if we are building machine, we have to really define good fundamental blocks. That was the reason all of this was created. And that was really, it's something called Entscheidungsproblem. If we have good axioms, so these building blocks are called axioms, then we maybe will find such a machine that will tell us, yeah, any stupid statement is true or false. And then we won't need any mathematicians, professors anymore, just we'll run the machine and it will print all possible theorems. How cool. Okay, yeah, so the set theory worked. But as you know, you've probably worked for some projects, and you know, at the beginning of the projects comes the business, says what you need, and of course then your answer is, oh, right now we'll do everything perfectly, we'll take Spring Boot, whatever, because the business goals are quite easy, and then we start, our system is clean, everything works perfectly, till the moment business comes again and changes the requirements. or refines them. Yeah, then the system, oh, you have to adapt something, then you put some hacks, more hacks, and this beautiful concept that you've created, your architecture falls apart, typically after 3 months. Yeah, so set theory prevailed a couple of years, so it was quite okay, but nevertheless then came such problems. Exactly the same story happened. Okay, that's a question stated by one of the mathematicians. Let's consider the set R of all sets that are not members of themselves. That sounds crazy. And then there is a question, is a R member of R? Don't dig into that. If you don't want to, we can rephrase it. In a city X, like Vienna, let's say it's Vienna, there is a barber who shaves all men who don't shave themselves. And by the way, only men who don't shave themselves. So he is like constrained to shave only such men. This statement is quite the same as the initial one, but in a human way. And then the question, should the barber shave himself? You see the problem. If he shaves himself, he is not allowed. So it's quite crazy, but that's something that is called Russell paradox. And that is thing that mathematicians found out, okay, in set theory, that's quite well working for defining what the natural number is, etc., and everything, even real numbers. We can't really fight with statements like that. Oh, it must be something broken. That's like, this crazy requirement. So the idea was the same as we do in the systems. Let's build some hacks. And the hacks in this case were more axioms. So they had like 6, 7 really beautiful, clean axioms at the beginning for the set theory. And then they've added through the years like 6, 7 more, I forgot the exact number, which are very crazy, right? The first 6 axioms, if you read them from the Wikipedia, are very clean, quite intuitive for everyone. All other are like, what are even those guys talking about? And those axioms were created to fight with such paradoxes. And even though from time to time happened new paradoxes, so there was a conclusion, maybe this set theory is not the best thing we can have. So, and there was this guy, Alonzo Church. Who has heard about Alonzo Church before? Oh, how cool. So you know everything. Yeah. So he proposed another idea. Let's don't talk about sets, let's make a fundamental particle of everything function, not a set. And then comes a question, how a function, because a function is something that converts from set to set. So in order to have function, we need to have a set. How stupid, yeah? But now, so this idea describes function without talking about sets. So sets with functions we've learned in school are not exactly the same as we think we will be talking today. And yeah, that's this presentation about. So new world of lambdas. Those functions, let's call them lambdas, just to make things complicated. So world wasn't created. There is no universe, nothing. What can you create? Is there any function that you can create? But you cannot create sets. No empty set. Can you describe a function in the world that wasn't created? No Big Bang, no flying spaghetti monster, whatever. Yeah. Yeah, what's an identity function? Yeah, but that's a great idea. That's the good answer. The answer is identity function, and what is this? That's a function that takes whatever returns the same. So you don't have to bring additional concepts to describe this function. So if in this world existed this presenter device, this identity function would take it and return the same. How cool? We don't have the presenter device, but we can describe if it existed. So generally, this function is the first step into the new world. How can we create things, yeah? So identity. And that's the way the mathematicians describe it. So how they write it. You will see it in the Wikipedia. It's just basically only to make things more complicated. I will explain this definition, but it's just a function, identity. Yeah. So what is a lambda? If you go to Wikipedia, you will see this, but let's define our functions this way. We'll use symbol lambda because it was just fancy symbol that wasn't used at that time. And then we'll provide something like variable. In this case, it's x, because every function needs something as an input. This time it's x. And after the dot, we'll say what we are going to do with that. So what's our definition of the function? That's basically how, in lambda calculi, you define the lambda. So just for a moment, once again, we are going outside this new world. For instance, the duplication. We are going to duplicate the x if it was a number, so lambda from x is x plus x. That's one function. Or if we define sinus, that's lambda from x is sinus x. Those are two valid lambdas. The only problem if we are building the mathematic, we cannot use plus or sinus because they were not yet created. We don't have them. So, that hurts. But we can go with that. So what we can use, in fact, is we can for sure we can use one operation, define lambdas, and inside of this expression, what we can do, we can reuse other lambdas, and we can use the most important operation of the functions that we have. It's so important that mathematicians choose the white space to define it. They were so scared to draw it. And white space means function application, only to make it complicated. So if you are thinking about sinus from x in lambda calculus, it would be in fact sinus space x, like this. So maybe let's take a look at this definition from the bottom line. Lambda from x, it's f, and applied with x. That's in the brackets. And then space means we apply it to y. It means if we do this application, in place of x here, will come y symbol, and we'll get f from y. That's the result of this application of the lambda. So that's very simple. You could rewrite it with the normal way you've learned from school, but we'll stick to this representation during this presentation for a moment. Yeah, so let's do it with Java, because you can go to that with in a Wikipedia. You will see a lot of these symbols. They are really great, but it will be hard for you to really, if you don't spend weeks on that, it would be really hard to find out what the hell is even going on there. So there is a way to make it all easier for you. Let's rewrite all these mathematics terms with Java. And the question is, what is in Java a lambda? What do you think? How can we describe with Java a lambda? You know, method, okay? Method in where? Okay, if we start with, we can discuss a method, of course. We can have a method. It would be what kind? How would be a name of method? What would be the name? Lambda, okay. Lambda. What would the method take? Okay, maybe I will make it bigger. What would the method take as an argument? X, okay. Okay, what would the method return? X, So, but it's in case of identity. But let's talk about interfaces. Can we define lambda as an interface? Okay, so I will help you, hopefully, with that. So let's think about functional interface defined like this. Functional interface, and we'll define it's lambda. Like this, okay? And this interface would have one method. One method, and maybe we won't call it lambda really. Let's call it apply. Because what you do with lambda, you apply it with something. And this method would take an argument of what type? Okay, that's the thing I in fact skipped. In a lambda calculus, we only have lambdas. Though all those functions I've presented, the only thing that we can put in place of x or y is another lambda. That's the point. And knowing that, we know that the only argument of apply would be in fact lambda. It's an interface that takes some lambda and what it returns. Exactly. That's so stupid interface. It's like, that's basically how we defined the fundamentals of lambda calculus in Java. That's this interface. It's interface lambda with one function that takes lambda and returns lambda. So this is the world of lambdas. We only have lambdas, nothing more. You cannot with this interface create anything else. How cool. And we'll go with that. So Let me define some lambdas for you. The first of them would be, and you will understand in a second what is this all about, because it's so easy. Identity is very easy to define. Like this, yeah? X returns X. So we can even display this. It would be stupid, but let's display it. That's displaying identity. Let's run it. Sorry, it's so slow because it's running on Maven. I never had time to change it to something else. So slow compilation for such simple code. But let's go farther. Please, yeah. And you see it displayed something stupid because system.out.println is just some hash of object. But we have already created one lambda. How cool. So right now we can do something more. We can do like this. Println identity, and we apply it with identity. Great. Yeah? Let's start it again. So we are playing right now with lambdas. We don't have much of them, but as you see by the code, it works. We had identity, and if we applied identity to itself, we get the same. How cool. It means identity works. So it's the first thing when we start to play with lambdas, we take this identity function, and then we apply it with something. But we are a little bit unlucky at the beginning. The only thing we have is just this identity function. So we are like playing, oh, let's play it with self. Yeah, sorry, you have no younger brother or whatever. Yeah, but we'll deal with that. So we are now stuck with this one unlucky lambda identity. Can we do some more? And let's go back to the mathematical world. Let's take a look at this definition. Lambda from x, after the dot is expression, and by the way, all of this is definition. The mathematicians don't use brackets, so basically it means this. So how can we read that? It's a lambda that takes some x and returns identity. How cool. We have identity already. What does it mean? If we apply it to some argument, we'll get lambda identity, and this argument will be generally forgotten. And then second time we can apply with something, and then we'll get this. So it's like how to create our second step in this world. That's another lambda. It's not identity. It's a lambda that produces identity and ignores the first argument. How cool. So if we for a moment have borrowed something from another universe, like maybe a trumpet and a tomato, you will see that lambda from x, if we apply it with trumpet and later with tomato, in first step, in place of x, will be trumpet given. But OK, we don't really have in the definition anywhere x. It means will be just ignored. So we'll get, at the end, lambda from y and the tomato as a second argument. And then, because it's identity, lambda from y is y, so lambda from tomato is tomato, we get a tomato after this operation. How cool. And then we can give back the tomato to this other universe that we have borrowed this thing. OK, so next step, other lambda. You see there is a slight difference. We take an x, and then we return something like this. Let's take lambda from y and return x. So something silly at the beginning. So let's play with trumpet and tomato. Lambda from x is lambda gives us lambda from y that returns still x. So if we apply it to trumpet and tomato, applying it to trumpet means in place of x, we'll write a trumpet. So after first step, we'll have this, but in place of x will be trumpet. So it will be the lambda from y, returning, and trumpet. And then still application of tomato. And as you see, this gives us at the end trumpet. So we have two different lambdas. Basically, by the way, very interesting fact. Lambdas only always take one argument. That's one argument functions. But as you see, we can effectively define something that is a two-argument function, because that's a composition of lambdas. How cool. So, and you see that we have two more different lambdas that identity. It's great. And even we can go farther. OK, here should be a space. Like lambda from x returns lambda from y that returns x applied with y. How cool. But the problem is I cannot present it with the trumpet or the tomato because it would destroy the trumpet or tomato. And I only borrowed those things from other universe, so I don't want to destroy anything. So let me play with that. That would be great. What will happen? So we have a lambda identity. So right now, let's just print it. And by the way, during this presentation, I will be trying to be I will be very strict to the lambda calculus. It means every lambda I am creating in the definition of lambda cannot use integers, floats, whatever. It can only use other lambdas created this way and applications of the lambda. So that's very, very strict subset of Java that I'm using. This Java without anything. But it would be very boring to play with, to not be able to display it. Because of that, I'm using some external library that helps me to transfer such terms into printable lambdas. So, and by the way, that's the library I've created, and this library is proven not to work correctly, even though I'm using that because I'm a wizard, so I don't care. It's just absolutely incorrect. Every mathematician can prove it instantly that it doesn't work. So how it works, if we define lambda identity, we can, with this smart display a mathematical term behind it. It's just like this. It doesn't use any reflection or whatever, because of that it cannot work correctly. But let's play right now with our lambdas. So funny lambda is like this. X that returns another lambda that takes y and returns x. Like we've seen that before with trumpet and tomato, so let's play with that. So we'll display this lambda. It's this funny lambda. You will see that the package works for. So we have this statement display. How cool. So there is this package that allows us to work with plain lambdas in Java and display them. But what for? What for? So let's define this lambda. It's a true. By the way, if you see, that's the same as a funny lambda. And by the way, it doesn't really matter. In world of lambdas, as long as they have the same representation, it doesn't matter how they are called. So basically, in any place of using true lambda or funny lambda, I can just replace them. But for a moment, I will use a true. And that there is a reason why I'm calling this a true lambda. Because if I create something else, the lambda that I would call false, you see there is a slight difference between false and true, how they work. Because basically, the true is the lambda that takes some x and then returns a lambda that takes y and still returns x. That's so. And a false is a lambda that takes x and returns lambda that given some y returns y. So basically, it's like a true is a function of two arguments that returns the first one, and the false is a function of two arguments that returns the second one. You will see how we play with that. So there is no coincidence that they are called this way, because we can create this lambda like this. And it's a function that, okay, let me put it here. It's a lambda and that takes some p and returns other lambda that takes some q and retains p applied to q applied to p. This way, okay? Sounds crazy, but that has the purpose. And by the way, I will display it a little bit differently, because if I had displayed it standard way with my standard smart display web, okay, maybe I will show you that. If I display this way, I will get, and is from x, y, because basically this displaying method doesn't know how the parameters are named. So in order to make the definition of and consistent with what I'm using here, I will use webp method. It means start displaying with using p, q, and so further symbols. It's just a trick, and by the way, it's not coincidence, because if you go to Wikipedia, they use the same symbols. So that's to make it more consistent what you read on Wikipedia. So we went so far, so let's do this moment. That's the most important part. We use and lambda we have defined, and we apply it. So apply means the first function. We will apply with a false. That's the first. That's a p argument here. And then we'll apply with it with a true. Something like this. And then we'll display it. Result. What will we get? You see? And result is what? Does it resemble something you've seen before? So, as you see, and with false and a true gives us false. How cool. Maybe we can do something. So let's do something. maybe we can see if it works. So we can use here true. So we'll see what happens. And you get something that looks like true. And by the way, it doesn't matter what are the symbols here. Maybe I can use here lambda with v, that w, which returns, I don't know, a1, which takes a1 and returns still w. So basically, it's the same as this funny lambda or a true. So it represents a true. So this time I will get what? True again. And of course, if I change here, for instance, to return a1, I should get something like false. So as you see, having these lambdas, I've created AND operation. So the basic of Boolean calculus. I have true definition, false definition, and they seem to work. How cool. So maybe to make it just more complete, we can go further with definitions like, lambda, just this lambda or is what? So what is a lambda or? Sorry, for a moment I am just stuck in my or is this. So it would be P that returns a Q. Oh, moment, I will do it this way because I never recall these symbols from the memory. So I'll do it this way. So lambda or would be like this. Or is a little bit different than P than AND. It returns this symbol, yeah? And then we'll display OR, and maybe let's play with that. So it's like a result to is OR, a false and a true, and we'll get this result to displayed. And of course, you should expect that it is, yeah, in this case, something like a true. So let's see if OR works the given way. So OR gives us, yeah, something that looks like true. How cool. Yeah, it's like works. So we have AND and OR, and you in this moment, you know, you have true, false, and OR. It means that, in fact, the Boolean calculus can be done. You can even go further and define, sorry for that, and define a NOT operator like this. And we can display what is not false. Not apply with a false means, yeah, let's see if it's true again. We should get and not false. Yeah, it's true. So we have basically with this very, very limited Java, we've recreated alternative Boolean calculus. It's completely useless, but it works. How cool. So right now, we can go more. So yeah, Boolean calculus is a true and false. Yeah, it's not complicated. Can we do something with numbers, like 0 or 2? So yes, indeed. So let's define 0 this way. 0 is by f and takes a function from f that returns identity. So by the way, it's the same as false. So in Boolean calculus, they already knew this decision that in C language was taken, that false is 0. How cool. So, but okay. But as you see, we have used different symbols here, not y and x, but f and x. And it's only to make it, yeah, that's a convention. You don't have to use these symbols, it doesn't matter. So let's define 1 this way. So we'll just display it and then we will see the thing. So, and 2 this way. So we have 0, 1, and 2. Let me, yeah. And let's just see this. So you see, oh, where is 2? Ah, 2 I haven't displayed. So to make it consistent, let me display 2. System out println 2. So in this convention, by the way, it's only convention, there is not one. We have 0, 1, and 2, and you see the number we represent is how many times f is applied to x. So it's to x. Like very simple. We can even define a successor operation. So incrementation this way. Looks crazy, but you will see that it works. And then successor from, let's see what the successor of 2, for instance, of 1 better. It would be easier for us. Yeah. So we have successor, we can even display this operation successor, and then we display successor of 1. And as you see, successor of 1 is indeed the same symbol as 2. So it works. It's easy. It works. So we've created the way to introduce natural numbers. So how cool. But natural numbers are only complete when we define other operations. Well, maybe let's see successor of 10. You will see how it works. And by the way, and once again, I borrow something from the different world. What does it mean, cardinals from integer? So I was really bored writing f from x with these all arrows. So this constructed for me. It's basically behind this. You will see there comes from this library. So it's my library that helps me with lambda calculus, but it's nothing more than simply this definition written so many times. And you can even see that. So successor from 10, you should see a lot of f's. I wouldn't even count them, but there are a lot of them. So 11 probably. OK, so let's go with something like this, plus. That's a really important operation, plus. And as you see, it's quite complicated. I wouldn't really try even to reproduce it from memory. So plus looks like this. We can display it. Once again, you see that I will display it, but with m symbol. Not a problem. And then let's do it this. Lambda A and lambda B. It's 6 and 7. And by the way, I'm not trying to use this. Maybe let me do that. So f from, sorry, just a moment. It's f that takes x done. And exactly that's the reason why I am using this. Sorry, not this. This is what I wanted to write. I wanted to write it returns f, apply x, and then f dot apply this, and then, yeah, you see that I am a little bit confused because it takes a lot of time. So because of that, I said to myself, no, I will really use this. Because I'm only at the moment of 2, so don't play with that. Let me do it simpler. I will play with that. So I will take the symbol 6. Because otherwise, as you see, constructing numbers by hand with this definition is very, very ugly. So, and time consuming. So let's display it. So to prove that it's exactly the definition of lambda as we already know. And then we'll do something like this, plus. So what is a plus? Plus a and b. We take a plus, this lambda, and we apply it. We apply it with a, and then we apply it with b, and then we'll display the result. Yeah, maybe even more. We can convert the result. There is such operation that to integer is an operation that converts and counts for me how many times f was called. So like, again, coming back to the different world, but only for debug purposes. So let's see if plus works. Exactly. So we have plus a and b, and now it's our job to count all those f's. It's 13, because I know this function counted it. You can count on your own. So we have plus operation that works. How cool! We have it. How great. So it's like natural numbers and plus. And you can see it's even more interesting, multiplication. So multiplication looks this way. And if we multiply a by 2, so we display it this way, we should get some result. And what's the result? Who knows what's the result? We can even convert it. Multiplication, easy. So as you see, finally we came to this one very important number, 42, with multiplication, but we really using Java with nothing. So really function definition and application, nothing more. We've recreated alternatively, yeah, almost integer. Those are not integers, those are natural numbers, but we are close. If you have, by the way, from mathematical perspective, if you have natural numbers, everything else is very easy. How to create from natural numbers integers and real numbers and etc. It's not a problem at all. So yeah, that concludes this part. So we have right now, yeah, what we had. We have Boolean calculus, we have numbers. How cool. But you can say maybe, that's easy because it's always forward. Let's do something more complicated. Like, I don't know, maybe some kind of algorithm. And that is exactly what I'm going to present you very quickly right now. Let's take a 9 as a number, so from integer 9, and see how, for instance, predecessor looks like. And that's really the function I wouldn't dare to try to read 3 in the morning. Really very, very nasty one. So that's predecessor, but we can see if it works. So decrementation of 9, so it's 9, and then we decrement 9. So like this. Ta-dam! Come on, Maven. Yeah. As you see, it is decremented because we have one F application less. How cool. So we have this. So we can now go both ways. So maybe we can create something, we can create subtraction. So it looks like this. It's not even that complication. Subtraction looks so. But we will play, in fact, with something more interesting than just subtraction. We'll play with if lambda. Let's represent something that is a algorithm step. If. What's an if? Who knows what's an if expression? If. So I will help you. If is very easy. It's something that takes a condition, and by the way, this must be something like true or false at the end, and then takes another argument that is what in case if it was true, and then takes the third argument, what it takes in case it was false, and then simply it calls true or false operation. So with this magical if lambda, this written, we have possibility to write ifs, and we'll use that possibility. So we can, for instance, create some such funny lambda like this. Is 0. And by the way, once again, this Boolean false lambda is simply in static variable extracted this standard symbol I'm using for false or for true. So this operation that takes something and returns anyhow identity. So this is 0 lambda. But we can go even farther, like less or equal or operation. And right now, but just those are definitions you can find in Wikipedia, but this one is really great. I call it even magical section. So let me do it. Magical section. What's autocall? That's a lambda that takes an x and return x applied to x. So it's very rude, nasty lambda because it simply someone comes and it says, do it to yourself. Yeah, really, the bad one. But it's useful. We can use it in something called y. And maybe some of you have seen this symbol before. Who had seen this symbol? Because it's very important, the fundamental symbol of the lambda calculi. It's y combinator or fixed point combinator. We're gonna need it because this is the symbol that allows us to construct recursive calls. Because there is a problem with recursive calls in Lambda. If we have a function in Java, inside of the body of the function, we can call the function again. Not a problem. That's the way we use recursion. If we define Lambda, suppose, for instance, that is 0 or less than equal wanted to call less than equal somewhere here, like here, for instance. The problem is, it's not possible because it's like if we call this symbol here, it's not yet defined because we define it here. So we cannot, inside of the variable definition, we cannot refer to variable again. So that's a nasty problem. And in order to fight with that, someone must have invented this fixed point combinator. So if we right now define such funny lambda, you see how it works. If lambda, let's check out the function. Take some r, take some n. By the way, this n is important. If this n is 0, we use if lambda, and is 0 as condition. Then we'll return cardinals 1 is simply this one definition that we used before. It's in static. Otherwise, that's what happens in case of true. Otherwise, what we do, we'll multiply n by something strange here, but by by predecessor of n. Yeah. Let me check if it compiles, because sometimes it, yeah. So we have this, and right now, any one of you has idea what I'm trying to construct here? So see, if it's 0, then I return 1. Otherwise, I will multiply n by something using n minus 1. Not really. Multiply. Factorial. So, exactly. So, sorry. If I use this y with g, I get something that I can call factorial. Let me show you that. So a would be 3. I will print this a. And then I will, in a result, I will print factorial from a. OK? And by the way, at the end, I will convert it. So this operation to integer lets me to convert. So let's see if it works. How cool. Factorial from 3. And if you see factorial from 3 is 6. How cool. It seems to work. Seems to work, but it maybe to prove that it works, we'll do something really nasty with 6. 6. Whoa. It's great. But if you check, it worked. It's exactly. So right now you see the power of this very limited Lambda, very limited Java, and power of Lambda. Using only definition of Lambda and using only function application, I've recreated even algorithms like factorial. So basically that's the proof. Okay, that's proved by, I would say, by example. But there is this proof that anything we can write on computers, we can represent with Lambda calculus. And basically it's proven long time ago that Lambda calculus and Turing machine are equivalent. So basically for me, it's Lambda calculus. It's an algorithm that works even on paper. It doesn't need CPU. It's so powerful. But you can do everything. It's proven. So that's cool. So maybe right now we can go to, and that's almost concludes my talk. We can go to this. If we can represent any statement, like theorem, like Pythagoras, whatever, Fermat theorem, with Lambda calculus, like because we have if, we can even construct something like if then, whatever. So let's represent this theorem as big Lambda. Then maybe we can just call it and say at the end if it's true or false. How cool. We just call it and we'll see if it's equivalent to true, then it means theorem is true. Otherwise it's false. And there comes a problem because people try to do this, but happen some lambdas like this, omega autocall. So I will just show you what happens. Stack overflow, exactly. It means there are some nasty lambdas that we cannot analyze with other lambdas because they are simply those recursive calls. Because, by the way, and it's the most important thing from today about Lambda calculus, no computable function can find out from other lambda if it's equivalent to true or false. Or basically, you cannot, having two complicated lambda, using another lambda, find out if they are the same. That's the problem. With something like this doesn't exist. And by the way, people on Stack Overflow do not care. They are working on that with a good result. They haven't studied maths, so they don't know it's impossible. So how cool. So there is, so basically, unfortunately, the problem isn't, the problem of this Holy Grail cannot be solved with Lambda calculus. And basically, it's just because this problem of equivalence is the same as halting problem of Turing machine. So you cannot, using a Turing machine, find out if another Turing machine stops. That's basically the same problem. And by the way, there is even a theorem from Kurt Gödel, you've probably heard about this, that no matter if we start with sets, if we start with lambdas, if we start with something else, I don't know, cheese, whatever theory we build, if it's good enough to cover the arithmetic, like plus or whatever, it cannot be complete. So in this theory will happen statements that are true, but you cannot prove them using this same theory. It's even, you can even, in this theorem, you can see how to construct that statement. So you can even exactly present such statement that it's true, but you cannot prove it. How cool. So summary from this talk. Lambda calculi, you can do it in Java. Why? Because it's funny. So we can prove that everything that's written on Wikipedia is working. It will be working on your machine. You can debug it. How cool. So I have skipped a lot of problem. Eager, lazy initialization, by the way, that wasn't the best definition of Lambda you could have. That was the easiest. I have skipped the problem of, for instance, typed Lambda calculus. So for instance, if I do multiplication, what if I put in place of argument m if? That would be stupid. But with this calculus, it's possible. So these problems were skipped. But generally, the thing I see from this, that whatever you can imagine can be done purely functional. Not that limited as I've presented here, because that's very, very poor functional. Pure functional. Poor, I would say, sorry. It's not even. So no excuse for you. For sure, everything can be. For sure, sometimes it looks crazy, so you don't have to use it everywhere. And if you want to waste a lot of time on Lambda calculus or mathematics, there are some good sources for you. So Wikipedia, I use the conventions that are on Wikipedia, so it's easy to follow this talk and recreate. So there is a good blog on the C# version of the same that helped me also. Basically, the guy was doing the same thing at the time I was doing, and he really went way, way farther with his blog. So I do recommend if you are interested. There is a great book from Roger Penrose, The Emperor's New Mind, which doesn't really say much about Lambda calculus, but says a lot about Turing machine, Gödel theorem, and things like that. So it's a very good book for inspiration about these things. And if you want to visualize your lambdas, you can use this package I was using, this Bedlam. By the way, it's proven that it cannot work mathematically, but on simple lambdas, it would work. This presentation you can find with tiny URL if you have at the end internet. So thank you very much.